of problems, all about kind of the idea of collective motion. I'm really interested in the idea of pattern formation and collective motion in general. And these are kind of the two different projects that I've had the opportunity to work on. One of them much more formally at the University of Delaware, and the other one due to an internship that I did. So I'm going to bring them up. I'm going to talk about them for you today. And feel free to ask any questions you have at any time. I'm pretty open to that. So the first thing I want to just discuss is that flocking occurs and collective motion kind of occurs frequently in every single organism. Basically, there are different ways that we communicate with each other. There are some amazing dynamics that happen. You see starlings that form these amazing patterns, moving and synchronously. Fish clearly flock together in schools. You even have some herding from sheep and some lambs. And even on the bottom right here, you have phytoplankton, which actually form these aggregations. And a collective behavior and collective motion is the idea that there's some form of a communication between individuals in a population, and then they kind of move in any certain way going to a certain direction. Maybe it could be circular, it could be going straight, it could be turning. There's a lot of different reasons why that occurs and how that occurs. And what I'm going to discuss today is kind of two different ideas of how two different types of organisms might try to communicate with each other to enhance this collective motion, collective behavior overall. And the first one I'm going to discuss is kind of this idea of a flocking mechanism. What does it mean to actually flock in general? Kind of the most basic flocking mechanism here. And this first part is actually more in tune to an internship that I did with the Army, actually back 2 years ago. And we're actually just about to submit a paper about this on trying to understand the structural orientation of how flocks kind of form and what the structure of the flock actually looks like in a long term here. So what I want to do is just kind of basically, one of the big questions when you think about flocking is, what is the decision in each organism's mind? How do they pick their next direction? Right? How do they pick their next direction? Where are they going to go next? So imagine you are in a 2D system here, and you are this red organism right here. I have all these different organisms here. You can imagine that this is a periodic box in this case. And how could you decide what direction you should be moving in overall? Now, the most simple model you can kind of think of is, well, let me take all of the organisms that are around me, find their average velocity, and then update my position based on their average velocity, and keep doing this over and over again. So for instance, if I'm this red dot, you can kind of imagine that I could take a circle around it, take all of the velocities of these different organisms here, take the average velocity, and then update my position that way. And every single organism does this. And if you keep doing this over and over and over again, you could probably see that eventually you'll be going in the same direction overall. And this is a very simple model. This is probably the most basic model you can come up with. And this is called the Vicsek model. And the Vicsek model, Thomas Vicsek back in the 1990s came up with this very interesting and very simple, discrete way to describe a flock in this exact way. So let me put some math to it. So I'm going to assume that Ri is the position of the ith organism here. Theta I is the direction. We're assuming 2 dimensions, it'll be a lot easier. V is your constant speed, and I'm going to have this noise parameter here, which I'll discuss in a little bit, which we know organisms aren't the best. They sometimes mess up their flocking or some way. There might be a little bit of stochastic noise there, so we're going to implement that too and see what that entails. But in general, the most basic thing is, how do I update my position? Right? How do I update my velocity and how do I update my position? My theta I gets updated by taking the average velocity of all of the organisms that are close to me, within a distance of r, I'm going to say. I just take all the average of all that. You can also have inclusion. You can take your own velocity into account there. And then plus some noise term. And this noise term is usually going to be picked from a uniform distribution between negative eta over 2 and eta over 2. This value of eta clearly goes from 0 to 2 pi. And after this, I have my updated velocity. I then update my position. Pretty simple in that way. I take my original position and then I update it with the cosine and the sine of that. So this is how I do this. We do this over and over and over again. And with this very simple model, we get some really, really interesting results. Now, before I kind of show you a more formal simulation here of what this kind of looks like, I want to think about how do we describe how flocked a system is overall. If I looked at a system and I want to see how flocked it is, what could I kind of, what metric could there be? And there's this metric called the order parameter, which is pretty standard. Tomas Vicsek came up with this back in his paper. And it's a measure of how flocked the system is. So basically all you do is you sum up all of the vectors, all of the orientations, and you take the average orientation. And if this value is 0, the system is completely random. They're all moving in completely opposite directions. And if it's exactly 1, the system is completely flocked, which means they're all going in the exact same direction. And what's really cool is this value usually starts around 0, right? If I'm just placing all these organisms randomly with orientation and position, and then eventually it'll go up to 1 and saturate, actually very quickly. So let me show you as an example simulation. At the beginning here, around t equal to 0, they're all just randomly oriented. And slowly but surely, after 10 time steps, we've already increased our order parameter from about 0.03 to 0.31. We've already increased it pretty fast. And then at T50, we're already at 0.675, and we kind of noticed that they've already kind of started to go in the same direction overall. And at T equal to 200, we're already almost at 1. We're at 0.9674. So that's pretty close to 1 at this point. So they're pretty much flocked. Now, to show you what the value of the order parameter does over time, this really increases really fast and then just kind of stays. Right, just kind of flatlines and gets incrementally bigger and bigger over time. And you can see that kind of really increases fast at the beginning and then slowly does that. Now, here was the problem that we kind of came up with, and the issue that we were trying to tackle is this does not tell the full story. And how can we kind of describe that? Well, let's take a look at the longer orientation, because if I'm taking a look at this, you would think that around like 200 or 300, this flock would be very similar to what the flock looks like over here at around time equals to 5,000. But this is not the case. What happens is, if you notice, the flock actually structurally, it was very, very clumped early on. Around here, they were very clumped. They kind of come together. They have to clump together to kind of start to reorient themselves. They have to get close to kind of interact with each other. And then at that point, they start to, over time, spread out. And they kind of almost fill the entire thing. It kind of almost looks like a uniform distribution again. And so this is not covered by the order parameter here. Or the order parameter only talks about orientational steady states, where in fact, we have to kind of consider that over time, the flock actually is doing the social distancing, as we've been talking about over the last, year or so now, kind of spreading out over time. And so this is very curious in how this does that, and the order parameter doesn't cover that. So what we're going to try to do now is try to understand how to effectively quantify, how can we quantify this structural change? Because the order parameter doesn't cut it. So how do we quantify this? So my collaborators, when I was working with them, I was working with a chemist and a physicist. I'm not going to start a joke. There's no joke that kind of comes there. I was working with a chemist and a physicist, and they come from a very different background of like fluids and molecular chemistry. And they came up with this idea that comes from molecular chemistry called the radial distribution function. It actually stems from this exact kind of problem in your head. What is the probability of finding a pair of agents a distance of r apart relative to the probability for a completely uniform distribution of agents? So imagine that I had a just completely uniform distribution of any agents randomly placed. How many agents would I maybe approximately see about a distance r away? And then do that again for what I actually see, and see that ratio. And if the ratio is greater than 1, it's more likely that we're going to find an organism. And if it's less than 1, it's going to be kind of that ratio will show that we're going to have a dearth of organisms there. So kind of this is called the radial distribution function. So we take this organism, we kind of see how far away it is, and we count how many organisms we see. I'm not going to bring you the full formula for this. I just kind of want to do this a little bit more kind of not lay back, but just kind of just to show you that the formula does not matter. What it kind of matters is that this value is 1 when a distance of r away is the same as a uniform distribution. We're more likely to see the same amount of organisms about r away. If it's greater than 1, we have an accumulation. If it's less than 1, we have a dearth of it. And what do these look like? So on the top here, you'll see the panels of t from 0 to 5,000. And on the bottom here, you'll see what this looks like. This value of g of r is in green. I've highlighted the purple here, the purple line right here is r equals to 3, which is our interaction radius, how, you know, the length of which we can find the average velocity around. And so we see at the beginning, this should just be 1, right? It's at unity because that's the uniform steady state. We would expect that. But after time equal to 100, they're all clumped together. Right? They have to clump together, they have to come together before they can start to interact and flock. And so you kind of see this massive increase in the value of the order parameter, of the value of this radial distribution function. And this means that they're all having to, structurally, they're kind of all together. And at this point, the order parameter kind of stays stagnant after this. But we see that this kind of radial distribution function relaxes over time, and eventually becomes to this structural steady state, coming back to this, where it kind of looks very, very much less, together. It looks much more uniform across the place. And what's really fascinating too, and this is what's really interesting, is that this value of g of r, this radial distribution function, has this discontinuous drop at our interaction radius. It's perfectly this kind of just, it drops, which is impossible to see from the naked eye. It's really impossible to see that from the naked eye what this looks like. And what's really cool is if I didn't tell you what this flock was, you could technically calculate the radial distribution function from this and maybe see this discontinuous flock and then gain a lot more information from it. And if you're wondering what this looks like for different interaction radii, you again, for a radius of 2, you get this drop at around 2, you get this drop at around 3, and you get this drop at around 4. It gets smaller and smaller and smaller every time, but we do see this discontinuous drop as the radius does increase. It starts to get smaller just because they don't have to clump as much at the beginning. So we don't see that as much. So this is really cool. And then what we wanted to do too is quantify a little bit more. We want to quantify, the radial distribution function does really good to describe what the interaction radii kind of mimics and what does that help with the organisms to do in terms of a structural aspect. But what about noise? How do we quantify noise? What is the noise doing? If we increase noise or we subtract noise, what is this actually kind of doing? And we came up with this other metric called the root mean squared mobility. It's a pretty common metric, and it quantifies how much noise affects the trajectory over the time. So kind of in the most basic sense, if I was at a time t and I wanted to predict where an organism will be after a certain amount of time steps, what is the way I can maybe predict where that would be? Well, if they're all going in the same direction, the easiest way to kind of predict this would be you take your organism where you're at now and then multiply it by the average velocity times t, right? And that can kind of predict maybe, where I'm going. Now, this probably gets worse and worse and worse as noise increases, right? Because the average velocity might be much more off in that case. So the prediction would be this value. That's my prediction, pretty nice. So the root mean squared mobility is actually the difference between where you predict it was and where it actually is, and the norm of that overall. And so this value, the root mean squared mobility, if you calculate this, we can maybe quantify how noise is really affecting the trajectory. If this is really off, then noise is really affecting kind of our prediction in this case. Now for standard diffusion, if I just was doing a random walk overall with eta equal to 2 pi, right? I'm just randomly going in every direction. You can actually calculate this explicitly. It actually is related to t to the -1/2. I'm sorry, just t to the 1/2. It's just the square root of time. And you can actually calculate the coefficient in front, this diffusion parameter. It's v0 squared, our velocity, speed, divided by 4. That squared divided by 4. And so our goal is to now try to understand what this value looks like as eta increases or decreases. And so in our work, v0 is equal to 0.5. So you can calculate this as just 0.5 t to the negative 1/2. And this is what the root mean squared mobility kind of looks like. Has the square root function. Now, eta is increasing over here, and you would think that it would just get worse and worse and worse over time until we kind of approach the eta equal to 2 pi. But that's actually not the case. What happens, and this was really, really weird to us, is that as eta increases, it makes sense that this increases, this root mean square mobility increases, but we actually reach a threshold at around 3.5. You can see around here. And then it's super diffusive. It's above this eta equal to 2 pi thing. It is a worse prediction. You get a worse prediction than if it was just random diffusion. And then it slowly comes back down from the top and finally kind of limits itself to eta equal to 2 pi. So it goes all the way up and then comes back down. You can maybe see it from this d parameter, right? It kind of comes back up and then comes back down. And now how can you explain this physically? What this physically is saying is the noise is small enough that the organisms are at least moving in the same direction. You can kind of predict what direction they're going in. They're kind of all moving in the same direction, roughly. But what happens is there's so much ballistic noise in each individual particle that they're all going in different directions than you're predicting, but the flock is still going in the same direction. So that's what's really fascinating about this. We had never seen this before. It's never been calculated in this, where you actually get this very difference from a microscopic and a macroscopic difference. The microscopic differences are much different than the macroscopic changes. There's not much macroscopic change. The microscopic decisions that every single organism is making is much different than what the whole system is doing. And we've quantified this here. And so what we're doing going forward, we're trying to understand this for different varieties, like different etas, different length scales, different domain sizes actually does affect this too. And we're relating this back to the order parameter and the radial distribution function overall. Now, with this in mind, now this is kind of the end of this part. What I'm going to talk about now is my main, kind of use some of these ideas in my main research that I do at the University of Delaware, which is with the idea of phytoplankton. And this is the work I've been doing since I was my first year here, actually, with Dr. Rossi at the University of Delaware. And so the idea of phytoplankton, I'm just going to briefly talk about the ecological impact that they have. They produce about 60% of our oxygen in the atmosphere. They're vital organisms to, any type of food chain, particularly in the ocean. But what has happened over the last several years is they've been forming more of these harmful algal blooms, or HABs, as you might know them as, or red tides, which what they do is they aggregate together, they overpopulate, and then at that point, they kind of block all the light going into the ocean, and so they have these massive fish kills, as you can see. This is a big problem actually in Delaware. The Delaware Bay, where I am, like about 2 hours south of where we are, there are these harmful algal blooms that have been popping up more and more and more, mainly due to sea level rises. Sea level rises and acidity levels and the heat. But what's really fascinating is they have to aggregate in the first place to make this happen, to overpopulate. And so one question that researchers brought to us was, can we model how plankton aggregate in the first place? How do they communicate with each other and then aggregate and come together? And that's what we're going to be working on here. I'm going to construct a model that kind of reflects the aggregation patterns of these plankton, and it kind of including how do they aggregate in the first place. And these are what we're using as a model organism, this organism called Heterosigma akashiwa. Akashiwa was actually Japanese for red tide. So we did experiments. I became an experimentalist. I was not an experimentalist. I became an experimentalist my first year. And we did some experiments mainly on light at the beginning. And we kind of see these really interesting patterns. They form these circular patterns. It's very different than like birds flocking, as I was kind of talking about earlier, or like maybe drones or something like that. These guys form pods. They form aggregations. They form circular aggregations after a certain amount of time. You kind of imagine that these are 2 inches by 2 inches. If you're kind of doing kind of a scaling here, if you want to know that, and about 1 inch deep, 1 centimeter or 1 inch deep around that area. And so at high intensity light, if we shine a lot of light on them, they do form these aggregations. After about 2 or 3 minutes, they'll start to do this, and they'll form larger and larger aggregations. These are about 60 minutes afterwards. If you form lower intensity lights, they kind of start to fan out a little bit more. They're not as clumped. But what's really interesting is we turned off the lights and they still aggregated. They still actually formed aggregations. They formed pods. So that means that they have to be communicating with each other to be doing this, because light, we thought light was their reasoning that they were actually forming these aggregations, but in fact, they're not. The underlying causes of this is actually something called chemotaxis, where they are actually moving towards a chemical. They're sensing. They can't see. They're just moving sporadically. So they have to be moving towards a chemical. And what's even more interesting is that they are producing this chemical. So it's called autochemotaxis. They are moving towards a chemical that they themselves are producing. And they're doing this as microscopic organisms, and they're quorum sensing and trying to figure out where the chemical is at every time. So we can form this model by just understanding chemotaxis, they're kind of going towards a chemical. And so I'll just kind of move along here to kind of describe some partial differential equations that we kind of use here. The first one is the chemical field. How does the chemical field evolve? The chemical field evolves, it diffuses throughout the system, and then decays, and then gets input by our plankton. So f of c is our deposition function. Plankton are depositing the chemical at a certain rate, depending on how much chemical they themselves sense. So you can kind of think about, if they sense something, if they sense their chemical, they will produce a certain amount of chemical dependent on that. And this f function, this deposition function, is unknown for plankton. But we have a couple different options that we're trying. One is that they just produce a constant amount of chemical. They just produce a certain amount of chemical always. Then there's this switch function where they produce an amount of chemical that's constant and then gets thresholded and gets switched off after they sense too much chemical, the C0 value. And then lastly, this linear switch, F3, where they produce a certain amount of chemical very precisely based on a linear thing as it grows, as they sense more, but then gets shut off. These are all biologically relevant. There's been many that we know about, maybe in ants, the idea of pheromones and stuff like that. Now, we have to know how they swim. How do plankton swim? They use this thing called run-and-tumble motion, where they move in a straight line, and then after a certain random amount of time, they flip to a different direction, which is also random. Now, in chemotaxis, if you're moving towards the chemical, if you're going on the chemical gradient, you are less likely to flip overall. So if you're but if you're moving away from the chemical gradient, you want to flip more so that you go on the chemical gradient. And this can be described very nicely by this probability here, where you kind of just do 1 minus the sign of this, the sign of both the chemical gradient and the direction that the plankton are going in. This is a very hard switch, though. It's either 1 or -1 or 0, and that's not biologically relevant. So what we do is we actually smooth this out with a delta parameter. So instead of the sign of x, we kind of do x over the square root of x squared plus delta squared, kind of smoothing that out. And this delta parameter, you can kind of think about as a chemotactic sensitivity. How sensitive are the plankton to the chemical? If delta gets closer to 0, they're very sensitive. If delta gets larger, they're not as sensitive. And this delta parameter plays a really important role. What do these simulations look like? Well, what they do is F1, F2, and F3, these different deposition functions, they produce very different results. At the beginning here, we see that these plankton, all of them kind of form these little aggregations at the beginning, as we do. But what happens over time is they become very, very different. F1 eventually forms this one singular large aggregation, kind of all together, just clumped up. F2, our switch function, that never really gets very aggregated. it almost looks labyrinth, like a labyrinth here, kind of a maze, and they kind of all connect everywhere. And then lastly, F3, they don't form circular or symmetric aggregations, they form these very interesting asymmetric aggregations. Now, I can go all day and look at this from the top and say, like, qualitatively, what do these look like? I want quantitative results. So how do we quantitatively compare simulations? There's really two aspects. We can compare the chemical, or we can compare the structure. The total chemical in the system, for instance, changes for each one of these. F1 actually stays constant the entire time. You can prove this, that it stays constant the entire time. F2 kind of slowly decays, kind of like an exponential function. I'm not going to say it's an exponential function, but it's kind of like an exponential function. And lastly, F3 really decays, but it has this very interesting kind of wavy pattern. It kind of has different plateaus and different periods where it decays over time. Total variation, how much is the gradient playing a role? Basically, the integral of the magnitude of the gradient is kind of the total variation. And we see that F1 has the largest variation, which means that it has the largest, steep drop-offs from our aggregations to our areas of dearth, of no plankton overall. We see that this again kind of mimics what we saw. The F3 kind of has a little bit less of variation, and F2 has kind of the least amount of variation because it's more smooth overall. How about structure? Well, we can use the radial distribution function now with plankton. And we see that over time, this radial distribution function changes and becomes much more dense for our individual with F1. Right? F1 was our constant epicenter function. If it's greater than 1, that means you can imagine that it's a lot more dense here overall. Has a lot more plankton around that individual plankton. What's really nice about this function, what we can use this going forward for, is to calculate the average size of an aggregation. The average size of an aggregation will actually be where this function hits the line y = 1. And so we can maybe calculate this over time to see how the aggregation sizes develop and what kind of different types of aggregations we might get. We can do the same thing for delta. I'm not going to go too much into this, but we can do the same thing for delta. But after a certain amount of time, if delta gets too small, it doesn't really make a difference anymore overall. As delta decreases here, we get less and less and less chemical overall. And the total variation, I've done this on a log-log plot, has a very interesting, it has a different type of, has two different time scales basically, as how much it increases, right? And then it kind of decreases overall. And we see that again, as delta increases, we get more variation, which makes sense. Organisms, if they have lower delta, they're easier to sense, so that we should expect that they should actually aggregate faster and more dense overall. And lastly, we can do the radial distribution function for delta. And unsurprisingly, as delta gets smaller, we get a more dense aggregation that around this beginning part here, delta actually becomes this value for G of R, becomes larger. And that's basically it. I think I've gotten around 30 minutes here, but I kind of want to just bring up like the ideas here that we kind of going forward. Flocking and collective motion, there are many different ways to simulate these. There are many different types of mechanisms. And a lot of times we can't understand their mechanisms from an outsider's perspective. We can't really do that from a science perspective. We can only understand what we're looking at. And because of that, metrics are really needed to maybe understand the microscopic decisions that every individual is kind of making in a system. And so there's kind of this really interesting interplay between microscopic decisions and macroscopic dynamics. And that's the ultimate goal of a lot of these flocking models, is to understand what's happening on an individual level so we can understand what happens on a much larger level and see the consequences of that overall. So there's a lot of different people. I thank like a million people down here. They're all very, very helpful to me. And yeah, I'll be happy to take any questions. And thank you again for inviting me. I really appreciate it.